While we're on the subject of formal charge, I can't resist telling you about oxidation numbers too, because they're really important. And if you've looked at chapter 10 in your text, which is an overview of chemical reactivity, you'll see that chemical reactions can be classified by whether they exchange electrons or not. And all of the fuel reactions that we're thinking about this semester are very definitely reactions that exchange electrons. And honestly, all of the really exciting reactions in chemistry exchange electrons. So while we're learning how to assign formal charges, we can just take a moment and learn how to assign oxidation numbers as well. Formal charges and oxidation numbers are both imperfect models of a complicated landscape of chemical bonding. They both lie in different ways. In formal charge, we assume that the electrons between two atoms are shared completely evenly. It's a completely nonpolar covalent bond. And in oxidation numbers, we assume the opposite. We assume that the electrons are not even shared at all, that the bond is essentially ionic, with the more electronegative element getting credit for all of the electrons. The truth, as we'll talk about this semester, as you'll see throughout your study in chemistry, is always somewhere in between, depending on the system. But both models have really important utility. Formal charge, as we've been talking about, is useful in predicting chemical structures. Which structure is the best? And oxidation numbers are really good at predicting reactivity. Given a particular molecule, in what fundamental ways is it likely to undergo a chemical transformation? So let's just take a moment and go over both formal charge and oxidation and the rules for assigning them. We'll practice these a little bit this semester. And later, when we're really zooming in on redox reactions in a lot more detail, we'll come back to these oxidation numbers. But if you've learned the basics now, then when we revisit this in a few weeks, it'll be a lot easier. So let's just take a simple example. Let's take hydrogen fluoride, HF. We can draw a quick Lewis dot structure. Fluorine has 7 valence electrons. Hydrogen is 1. We have a total of 8 valence electrons to distribute, so the Lewis dot structure will look like this. In formal charge, we've already gone through that. Formal charge. Each atom is going to be assigned a formal charge, and we're going to use the rule as the number of valence electrons minus the number of non-bonding electrons minus the number of assigned electrons. And interestingly enough, oxidation number is the same. It's the number of valence electrons minus the number of non-bonding electrons minus the number of assigned electrons. All that differs in these two formalizations of bonding is how we assign the electrons. So we'll see how that works. So as I just mentioned, in formal charge, we're going to assume that the electrons are shared evenly. And so fluorine gets 1 electron in that chemical bond and hydrogen gets the other. And in contrast, in oxidation numbers, we're going to assume that the more electronegative element gets all of the electrons. So the green is for formal charge. The pink is for oxidation numbers. So when we assign electrons, when we're figuring out oxidation numbers, fluorine gets both of them and hydrogen gets none. So let's see how that would add up. So the green is for formal charge. So hydrogen has 1 valence electron. It has no non-bonding electrons. It gets assigned 1 because we assume that bond is shared evenly. So hydrogen has a formal charge of 0, and fluorine has 6 valence electrons 7 valence electrons. It gets assigned, it has 6 non-bonding electrons. It gets assigned 1. So fluorine also has a formal charge of 0. So neither atom has a formal charge. The sum of the formal charges equals the charge on the molecule. It's a neutral molecule, so that's all good. That tells us we also have a good Lewis dot structure. Oxidation numbers are just a little different. So now hydrogen has 1 valence electron, but it gets assigned no electrons. Remember, both of those electrons get assigned to the more electronegative element. So hydrogen has an oxidation number of +1. And then fluorine has 7 valence electrons minus 6 non-bonding electrons, but it gets assigned both of those electrons. So fluorine has an oxidation number of -1. Again, the sum of our oxidation numbers, this is +1 minus 1, equals the charge on our molecule. So we know we've assigned oxidation numbers correctly. But what this tells us when we start to think about reactivity is that fluorine with an oxidation number of -1 has a noble octet. And so that's going to be a guide to us that fluorine in hydrogen fluoride already has the right number of electrons. And so whatever kind of reaction this undergoes, we're not going to expect to see it be a reaction in which fluorine gives up electrons because it's already satisfied its noble octet. So we'll spend more time thinking about the significance of oxidation numbers when we get to this section later in the semester. But since the basic rules for assigning formal charge and oxidation are so similar, oxidation numbers are so similar, just thought it'd be good that we go ahead and learn the oxidation numbers while we're on the subject. And just remember that formal charge assumes the electrons are shared equivalently and that it's good for predicting structure. Oxidation numbers assume that the electrons are shared unequally, with the more electronegative element getting credit for all of the electrons in the covalent bonds, and oxidation numbers are useful for predicting reactivity.